I did fine on your midterms. Today we'll be talking about sorting. So if you want to link the slides, feel free to visit the link we have here.
It's also at the bottom of every slide. So if you want to see it, wait.
Yeah, so as always, we'll be giving out a raffle, an Amazon gift card to one attendee from this contest. So let's see who this week's winner is. Is Eduardo here?
No.
Yes.
Well,
Steven? You here?
no. Okay. Grace. Grace? I just keep holding the lines.
Is Arnav here? Okay, maybe the most efficient way to do this would be to remove everyone's
Okay.
Okay, is Christoph here? Never mind. I was gonna say just give it to you. All right, David. Congrats, Christoph.
I have your contact. Yeah. Okay. Oh,
So just a reminder, CS Town Hall is next Wednesday, November 9th. So if you guys are interested in going to that, feel free to fill out the RCP or the survey.
Oh yeah, like take maybe 5 minutes to fill out the survey. This is basically our way of communicating our opinions about the CS curriculum to the CS department. And then during the CS town hall, they're gonna pull out all the requests by students. Like they're gonna the faculty members are gonna discuss the top requests one by one during the CS town hall. So if you're interested in knowing what the CS department wants, or what the student body wants, and then if you have any suggestions for the CS department, definitely fill out the survey and then consider going to the town hall. It's a great opportunity to decide what you want to do in the future.
If you've taken one or taken one since this one.
So yeah, take 5 minutes to maybe fill out the survey and RSVP if you want.
When to use sorting and what is sorting. Next, we're gonna do 2 example problems, and we're also gonna cover big O notation. So if you haven't heard of that before, we're gonna give a quick introduction today, and then all of our normal stuff like a sneak peek and then our contest. Okay, so sorting, as the name implies, is basically taking an array or a collection of objects, and then we're going to sort them into the right position. So for example, if you have 1, 5, 4, 2, 3, then if we sort them in ascending order, it becomes 1, 2, 3, 4, 5. But you don't necessarily have to sort an array of integers. You can sort anything you want that has a natural ordering. So for example, if you have characters, A, C, B, then you can sort them and it'll become A, B, C. Okay, so there's a ton of different sorting algorithms. All of them achieve the same goal of leaving the array sorted. So algorithms are called bubble sort, insertion sort, merge sort, etc. At an introductory level, you don't really have to understand what each of them, how they're implemented. All you have to know is that as you can see here, they basically go through the array, perform some number of operations, and in the end, they leave the array sorted. And another thing you should know is that C++ uses intro sort. You don't have to know how it's implemented, but basically you should never use your own sort. Just use the built-in sort because C++ always uses the fastest one. Okay, and here we have a video.
So quiet.
Now, it's hard to get a job, right, as president, and you're going through the rigors now. It's also hard to get a job at Google. We have questions, and we ask our candidates questions, and this one is from Larry Schwimmer. What you guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this? Okay. I didn't see computer science.
We've got our slides in there.
Well, why not? Let's ask a different interview.
Okay, so now we're going to talk about how to actually sort it in your program. So to sort, all you have to do is include the header algorithm. And then inside of your program, if you have a vector, the way to sort it is just to sort the vector.begin and then vector.end. And so if you haven't seen .begin and .end before, basically what it does is it returns like an iterator to the beginning of the vector and to the end of the vector respectively. And so what that tells the program is that you want to sort it from the beginning to the end. So for example, if you wanted to sort the first 3 elements, you would do sort vec.begin and then vec.begin plus 3. So if that's a lot of stuff to remember, all you have to do is just sort it from the beginning to the end using this function. Okay, so now we want to ask like when to sort and why would we sort. So it's pretty obvious that you should sort when the problem is about sorting. So for example, if the problem asks you to find like the kth smallest number or like the kth element in order, then chances are you would want to sort the array. Another case is when the elements of the array have an intrinsic order or when the current order of the array doesn't matter. So for example, if they give you the array in some arbitrary order that you don't need to remember, you can just sort it. And then that allows you to do a bunch of different algorithms. So we'll show you a few examples later to make this a bit more clear. Okay, so when and why. So sorting is usually used in order to find the nth element in an order. And a lot of different algorithms require the array to be sorted before performing the algorithm. So for example, a few popular algorithms would be like Dijkstra's, Kruskall's, or Prim's algorithm. It's also a form of pre-computation. So after you sort the array, you don't have to resort it. So you can just do it once and then the array will always be sorted. And so it's similar to why you would clean up your desk. It's because it makes the later task easier and you only have to do it once, or at least like once for now. Okay, so we have our first example here. You can feel free to go to the link, but the general summary is that you're given 3 numbers of a 4-number arithmetic sequence, and you have to find the missing one. So for example, if you have 31, 32, 33, the answer would be 34. Or 30. Or 30, yeah. So feel free to read it and then try to come up with a solution.
Just look at concept.
Did I set the wrong date? Oh, sorry about that. That is right?
Any ideas, thoughts, approaches? I guess we'll talk about our approach then. So the simple solution would be to just use a bunch of if-else statements, because all the different possibilities are, you can just write them all down and then check each one. But the issue is that this would be very messy and time consuming, and nobody really wants to write that many different cases. So the better solution would be to sort it, and then we can find out where to insert the fourth number. So for example, after we sort 32, 31, 34, we get 31, 32, and 34. And so in this case, it's immediately obvious that our missing number should be between 32 and 34. Another case would be after if we sorted, those three form an arithmetic sequence, in which case we would know that the fourth number would just be the largest number. So does this all make sense, this approach here, why we apply sorting? Okay, great. Okay, so now we're going to talk about big O notation. So just to see, like who here has not heard of big O notation before? So everyone has like a general idea of what it is. Very great. So mathematically, O of f of n basically represents the asymptotic upper bound of a function of n. So the most common time complexities, at least for competitive programming, are O of n squared, O of log of n, O of n, and O of n log n. So basically what it tells you is it tells you how many times you have to go through the entire input data using a specific algorithm. And so what we do is we ignore the coefficient and the lower order terms. So we'll show you an example on this slide. So just looking at this example here, we iterate through a loop n times, and on each iteration we add the ith element to s. So does anyone know what the time complexity of this function would be? Yeah, and why would it be O of n?
It's like the condition for the
Yeah, exactly. So on each iteration, we do one operation. Addition is known as like an elementary operation, so it's just like one time unit, I guess. So when n gets large, the one becomes negligible. So O of n plus 1 is the same as O of n. As another example we have here, so we're iterating from a equals 0 to 4, and on each iteration we iterate through I equals 0 to n. And then on the inner loop, we add the ith element to s. So in this example here, does anyone know what this time complexity would be?
So we just for like 4n, which then
So basically we know from the previous slide that this loop here is O of n. And so in the outer loop, we run the inner loop 4 times. So our total number of operations would be 4 times n. And so again, in big O notation, we ignore the constant term. And so our final time complexity is O of n. So this program has the same time complexity as the previous program, but that doesn't necessarily mean they run at the same speed, because again, we ignore the constant coefficients. Okay, what about this example here? So the difference between this slide and the previous one is that instead of iterating from a equals 0 to 4, we iterate from I equals 0 to n minus 1. So what would this be? Yeah, exactly. How do we know that? Yeah. So this inner loop is again O of n, and the outer loop is running the inner loop n times. So our total number of operations will be n squared. And so the reason why we ignore lower order terms is because as n gets really large, the n squared dominates the n, and so we really only care about the biggest polynomial or the biggest function, I guess. So we can use the time complexity to estimate what kind of algorithm we need to find. So as an example, if we have the input size is 10 to 8, then oftentimes that means that we need to find an algorithm that's O of log n or O of 1. And this is because if you try to run, for example, an n squared program where n is equal to 10 to the 8, then you're going to have to run 10 to the 16 operations, which is going to take your computer several years to run. As another example, if you have n equals 10 to the 5th, then you can use O of n log n, but you can also use any time complexity that's smaller than that. So you could do O of n log n, you could do O of n, O of 1, or O of log n. So you don't really have to memorize this chart. As a rule of thumb, the total number of operations you could do is around 10 to the 8. So, for example, if you have n equals like 100, then n cubed would be around 10 to the 6, and so it would be good enough. But if your total number of operations exceeds 10 to 8, then it's probably going to run out of time. Okay, so in this example here, we have two inputs. We have n and m, and both of them are from 0 to 10 to the 5th. And so in this case, let's say, for example, we try to do a nested loop where we iterate from 0 to n, and on the inner loop we iterate from 0 to m. So that would be O of mn. And so in this case, that would be too slow because then our total number of operations would be 10 to the 10. And so that exceeds 10 to 8. But instead of that, we can do, for example, O of n log n, or O of n log m, or some combination of those two. In our second case, we have n is less than 200. And so in this case, since n is so small, that gives us a lot of room to try out different algorithms. So we could do O of n squared, O of n cubed, or yeah, any of those functions that aren't really like that large. So does this make sense to everyone?
Okay, now we're moving on to second example problem of the day. It's called but basic programming 2. It's it's different from the normal embedded programming problems you would see in the contest, in the sense that it has like 5 different tasks, and then each one of them is independent of the other. So if you want to like submit the problem and then get an AC, you have to write out a solution for each one of the tasks. However, for this purpose of today's workshop, we're gonna just go through them one by one rather than going through them like all at once. So let's, yeah. Oh yeah, I'll give you guys like 2 minutes to read through the problem statement. And then we'll start with task 1. See if we can come up with a solution to problem 1. Okay, so has everyone read task 1 yet? Really, that's enough time to read through task 1. Basically, for this problem, you want to find x and y, 2 numbers from a given array, such that these 2 numbers add up to a 7,777. This is like a very standard interview problem, right? You guys probably have already seen it if you've done lead code before. 2 sum. And the idea of this problem is, if you simply check every pair of numbers from the array, there will be too many pairs to check. Like for example, in this problem, the specification tells you that n can be up to 200,000, and if you square that, that would be 40 billion checks in total, which is way too slow for our normal program. So what do we do? Well, can we come up with a better solution, a faster solution? I'll give you guys like 5 minutes to try and implement a solution using sorting. See if you can come up with a solution that is faster than order n squared using sorting. Oh yeah, by the way, sorting is order n log n. So it's faster than n. Okay, I'll go over the solution. So you might know some better solutions than sorting for this particular problem, but for the sake of today's workshop, because we're focusing on sorting, we are going to go over this two-pointer solution, which is very useful in competitive programming as well as coding interview. Now, the two-pointer solution requires you to sort the array at the beginning. So it only works when you have an array that's already sorted. Now, initially, you have the array sorted and you initialize the left pointer and the right pointer, each pointing to their corresponding ends of the array. And then say, for example, your goal is 13. You want two numbers to sum up to 13 in this array. Starting off, you look at the left with the number pointed to by the left pointer and the number pointed to by the right pointer. There are 1 and 8. They sum up to 9, which is smaller than 13. So you know that because 8 is already the largest number in the array, right? And then 1 plus 8 is still not large enough, which means 1 is probably too small. Like no matter what the other number is, 1 is too small to reach this target. So we can safely just move our left pointer 1 stop to the right. And then basically we're eliminating 1 from our search space. We know that 1 can't possibly be the number we're looking for, so we remove it. Now, what about 2 and 8? It's still too small. So we remove 2 as well. 4 and 8, they sum up to 12, which is still smaller than 13. So we remove 4 as well. Now we have 6 and 8. Notice that 6 plus 8 equals 14, which is larger than 13, right? And we've tested all the numbers that are smaller than 6. We know that 8, no matter which number pairs up with 8, it's always going to be either too small or too large. So 8 can't possibly be the number we're looking for. So we can eliminate 8 from our search space and move our right pointer 1 stop to the left. Now we have 6 and 7. They add up to 13. So we've got our answer to this example. Now, how do we know when to stop this algorithm? Well, first of all, the trivial answer to that question is when we found our target, right? If we found 2 numbers that sum up to the target, we can stop the algorithm because we've reached our goal. And then what if no numbers in this array sum up to the target, right? How do we know that we've searched through all pairs of numbers and then we can't find 2 numbers that sum up to the target? Well, in this case, notice that like in the prior example, we have 6 and 7 side by side when they're adjacent, right? Turns out that they add up to the goal. However, if they don't add up to the goal 13, then we would have to move either one of the pointer, like either the left pointer 1 stop to the right or the right pointer 1 stop to the left. And the end result is that the 2 pointers are pointing to the same number, effectively limiting our search space to only 1 number, which means it's not possible. In this case, it means it's not possible to find 2 numbers that sum up to target. So in that case, we also want to terminate our algorithm. Right, on the right side, I have the implementation of the solution posted here. So at first, you want to sort the array using the sort function in C++, and then you set a Boolean flag, basically telling you, okay, whether or not you've already found the pair of numbers you want. And then you initialize the left pointer to 0 and the right pointer to n-1, while the 2 pointers are still pointing at different numbers. If the number on the left, the number pointed to by the left pointer and the right pointer sum up to 7,777. Well, while they're smaller than 7,777, we want to increment the left pointer, so moving it 1 stop to the right. If the sum is greater than the target, we want to decrement the right pointer. And then if the sum is equal to the target, we want to terminate our loop and output the result. So at the end, we print yes if we found the pair, and no if we can't find the pair. Also, in case you're not familiar with this syntax, it's the ternary operator in C++. It basically means it checks whether or not found is true. If found is true, or like the variable in front of the question mark is true. If the variable in front of the question mark is true, then it returns the evaluates to the first value in the second part of the expression. If the variable is false, then it evaluates to the second value in the second part of the expression. It's basically a shorthand for if else. Now that's the first task of this problem. Let's move on to the second task, which is to determine if there are any duplicates in an array. So again, ignore approach 1 as it's not important for today's workshop. If you know what a hash set is, then good for you. That's yet another better solution than sorting. However, for today's workshop, we are going to use sorting to help us accomplish this goal. Take 5 to 10 minutes. See if you guys can code up a solution, or like come up with a solution and then perhaps even implement it. Do you need to link to the slide? Hopefully you've had enough time to think about the problem and potentially you have written up a solution for this. Does anyone need more time, or is everyone good? Good. Okay. One key observation to this problem is that duplicates after you sort the array are always adjacent. So look at this array, for example. The 2 and 2 are adjacent to each other, and now the 5s are together. So using this fact, we can solve this problem. Because this problem only asks us to find duplicates, right? So once we found one pair of duplicates, we're done. So what we can do is we can simply just iterate through the array and then check all adjacent pairs of numbers, see if they are the same. Now this is the code that implements this idea. So initially you sort the array, and then you set up a flag contains duplicates. This flag tells you whether or not you found a pair of duplicates. And then you iterate through the sorted array. Check, wait. Okay, that's right. So you iterate through the sorted array, and then you check at each index whether or not the previous element is the same as the current element. If they're the same, then you found the pair of duplicates. You break out of the loop, and you print that there's duplicates. If they're not the same, then you continue until you've reached the end of the array. If at that point you still haven't found any duplicates yet, it means that the array contains only unique numbers. This is task 2. Now, we know how to find duplicates. Do we know how to find the majority element of the array? Say if you have an array, right, the majority element is defined as an element that appears more than half of the time. So, for example, in this example, you have an array of length 7, the majority element would have to appear more than 4 times, more like at least 4 times to be considered the majority element. So imagine if you are voting for something, right? You would have to have a majority to for your like idea for your bill to pass, and that's what majority element means. So task 3 basically asks you to find the majority element of an array. See if you can figure that out how to do it. Solving this problem requires it's basically it requires the same technique as the one we used for task 2. So take 5 minutes and then see if you can implement this solution. Okay, so how's everyone doing in this task? Doing good? Basically, we use the same idea from task 2. Well, if 2 numbers are the same, they're adjacent. So if there's majority element, they're all clumped up together in one consecutive chunk. So after sorting the array, we can simply just traverse through the array, keeping count of the number of times we've seen the current number, right? If this number is greater than n/2, then we found the majority element. If it's never greater than n/2, then we know that there's no majority element. So an interesting question that I want you guys to think about is, after sorting the array, what if the array has a majority element? Then what would the middle, like the element in the middle of the array be? Would it be the majority element? Is it guaranteed to be the majority element? Okay, I'll let you think about that. Here's the code implementation of the solution. So you sort the array first, and then you set a current count to you set current count to 1. Oh yeah, you set the current count to 1, and then starting from the second element, you check whether or not it's the same as the previous element. If it's the same, you increment the current counter. Otherwise, you set it back to 1 because you found a new element, and it's and then in the end, if current count, oh yeah, every time you switch to another, oh yeah, so every time you update the current count, you check whether or not the current count is greater than n/2. If it's greater than n/2, we found the majority element, so we break out of the loop and then we print it out. Otherwise, we do nothing. So now we have the 4th task of this problem. It asks you to find the median of the element, the median element in the array. This is, in my opinion, way simpler than the previous 3 tasks. See if we can implement this in 3 minutes. Now I'll go over the solution. So for this particular problem, one thing you need to notice is that the length of the array actually matters how you find the median, right? If the length of the array is odd, then you only need to find the middle element, which is at index n/2. If the length of the array, is even, then you would have to find the middle 2 elements and then take the average of them by definition. So that's exactly what we do. Here's the implementation. Sort the array. If n is odd, then we output the n/2 element of the array. If it's even, then we print out. Oh, we need to print out both. I guess we need to print out both for this particular case. So in task 5, it asks you to print out the integers between 100 and 999 in sorted order. So let's say you have an array 1, 962, 100, 2, 110, 5, and then 1000. The question asks you to print out 100, 110, and 962, omitting all the elements that are not in the range. And also, you're asked to output the elements in sorted order. So if the problem asks you to sort it, what do? You sort it first. And then once you've sorted it, you can just print out the elements in order. Simple as that. Here's the code that does it. You sort the array, and then you iterate through the array. If you see an element that's in the range, you print it out. Otherwise, you do nothing. And finally, in the end, or you need to print a new line. I guess it doesn't really matter, but for consistency, you want to do that. Okay, so that concludes the workshop section of the lecture section of today's workshop. I will give everyone like 3 to 5 minutes to fill out this feedback form, and then we'll have our okay. Please fill out the feedback form so that we know what to improve on in the future.